So it is assumed that there will be some talks, remarks about the statements which were formulated today during the talks, and about the statements which were not formulated and have to be formulated. So the first speaker for this program is Vladimir Zakharov from Landau Institute, who will say what does he think about various forms of collapse in partial differential equations. Okay.
Probably I will give you a little bit more, some more general remark. First, but certainly I will speak about the dynamical system with infinite number of degrees of freedom. I am sure that in the next century they will be in the center. All right, thank you. Because actually, for Neumann said once that mathematics is enormously efficient, and it's a mystery why it's so efficient. I'm sorry, yes, Wigner, excuse me. Eugen Wigner said that. But let me argue with this point, because I can formulate two very simple natural problems which are absolutely unsolved, and so far there is no any approach for solution of this problem. They are very practical both. First, suppose we have a big tube, and one push a big tube, probably from oil, and not long or not, it's not that enough. Not that important. It's just important that it's big enough so that and we one pump the liquid through this tube, and suppose that viscosity tends to 0. So suppose it's a superfluid helium. And in spite what's known experimentally, that there is in spite of this fact, there will be a gradient of pressure along of this tube, a gradient of pressure, and this gradient of pressure, dp by dx, has a finite limit. Is some constant lim of this. A constant if viscosity tends to 0 is some finite value. It doesn't depend on viscosity. And then it's proportional to the following thing. It's proportional to v square, q square. Q is just a flux divided by r. Now, r is a characteristic radius. And so there's some coefficient here. This coefficient is known from experiment, but absolutely there is no way to calculate it because there was a turbulence inside of this tube. And what's interesting that in a sense, because it's proportional to q square, the pressure is not linear in the flux, but it's quadratic. If you like to pump twice more energy, you have to spend 4 times more. You want to pump twice more fluid, you have to spend 4 times more energy. This is the first problem, which is unsolved. Another problem. No, not just for liquid, for water. For water, this coefficient is universal. It doesn't depend on what kind of fluid it is. The next question is.
Viscosity goes to 0, but it doesn't have to be too small to start conversion. Viscosity goes to 0.
Yeah, viscosity goes to 0. In the limit of when viscosity goes to 0. Yes.
Then you say limit starts reaching.
Yes, the limit is constant. Another problem is also very natural. Suppose you have a fluid which is heated from below, and it's heated from below in some gravity field, and there is some heat expansion coefficient, so that the heated fluid is more light than the cold fluid. And again, there is some heat conductivity coefficient, and suppose that heat conductivity tends to 0. Again, the flux of heat tends to constant value, not to 0. And not necessary to explain how important this problem, for instance, for meteorology or for astrophysics. And again, there is no way to solve this problem so far. And anyway, actually, when in a process, when what's known experimentally, when in a process when kappa tends to 0, the qualitative picture changed many times. And this system is the qualitative behavior inside of this slab could be very much. There are a big variety of and. Of course, if kappa is small enough, the steady state is unstable. If kappa is large, that's okay. Everything is very simple. But then it starts in a unstable. Then there is some structure above instability. The structure became unstable itself. Then they develop a different type of turbulence. And the turbulence change its character. And finally, what's happened? Then the very narrow films of hot fluid, they go up and they behave, they curve, and so it's a very geometrical problem. The problem is how to describe the dynamic of very thin film in this fluid. And this is a fascinating problem. So it's a very difficult problem. I have formulated more simple problem, more close to pure mathematics. Again, still unsolved. Suppose we have a fluid in a just ideal fluid with no gravity, with no viscosity, nothing, just ideal fluid put in outer space, without gravity, without anything. And suppose even that, no viscosity, nothing, but suppose even that the motion is potential, it's very simple motion. And the problem is, suppose we make some push, so we created some initial perturbation. What will happen? Will the problem smooth or not? The conjecture is not. And again, it's possible to. Recently, we solved this problem in some very special case when in the moment of typically the behavior is following. It will produce an outburst, produce some kind of spray in a finite time, and it's difficult to solve this problem in the general case. It's so far impossible problem. Recently, with Kuznetsov, we solved this problem in a very special case that when in the moment of collapse, the surface is flat. But of course, motion happens here. So we used expansion in the small parameter, which is the angle. And so it's happened that it was a kind of well is filled, and when the surface becomes flat, at some point they produce the outburst. Yes, it's a finite time singularity. It's an earlier equation, more or even in potential flow, but with free surface. And Yasha said about singularity in Navier-Stokes equation. But even more simple problem, more crude problem, singularity in Freiburg of the Euler equation. It could be. It's still open. It's still open. Yes, but with free surface. But suppose it's filled. Yes, if have no surfaces, of course the potential flow make no sense. So this is, and I think that. But if we study, but in all these cases, the problem is essentially nonlinear. So there is no any linear approximation. So there are the big class of problem where the system A consists of linear and nonlinear part. For instance, surface waves in presence of the same problem in presence of gravity. If the gravity exists, this system A is a system of oscillator of infinite number of degrees of freedom, and this system is more doable. It's more pliable from viewpoint of more traditional mathematical method, but still they produce a lot of very interesting and difficult problems. So I finished.
Thank you very much. We don't have too much time. Other questions?
Серьезно? Окей. Я должен.
Who can say interesting things about Euler equation, which was mentioned by Zakharov?
Okay, so consider the motion of an ideal incompressible fluid. No, ideal incompressible fluid is in fact very slightly compressible and slightly viscous fluid. So it is a common limit of these more complicated systems, and as such is maybe more fundamental. What is known, the first fundamental fact, is for dimension is 2, if given initial velocity field which is sufficiently regular, then the solution exists for all t. So solution exists globally. Now if we consider the motion in a bounded domain, for n equals 3, its solution exists for module t less than some time. No, actually this time where the solution exists by sure is the time when nothing interesting happens. Therefore it still exists. No, yes, and what is later beyond this time, it is unknown. So these two cases are fundamentally different, and the connection with dynamical systems, more or less non-trivial connections, are known to me only for this case. So let me restrict with two-dimensional motion. So in 2 dimensions, this is the M is the flow domain. This is actually an infinite dimensional mechanical system whose configuration space is the group of volume preserving diffeomorphism of this domain, and the velocity is velocity field. So the state of the fluid is given by the pair G and U. Here is G is element of this group, and U is a vector field, which is incompressible and tangent to the boundary. And we have everywhere defined in the space of smooth diffeomorphism velocity field, everywhere defined dynamical system, which I am not going to write because it doesn't help. So now we have meaningful dynamical system in this phase space. And the problem is, what are the properties of this dynamical system? All the questions which may be posed for dynamical system may be posed here. No, first of all, what are the geometrical properties of this space, of this configuration space, diffeomorphism group? No, the first result, which is one that was obtained only recently, that diameter of this group is infinite if n equals 2. This was proved by Eliashberg and Rato in 1990. In the case in three-dimensional case, I have proved that it is finite. So now, if this is a unbounded metric space, unbounded infinite dimensional manifold, so the next problem, how does it look? Actually, they proved that there exist pairs of points which are removed from one another, but it says very little about the structure of this manifold. So we are interested, it is, if it is unbounded structure, so the most interesting is structure at infinity. Yes, now there is a framework for discussion of this, which was created by Gromov to consider the asymptotic space or asymptotic cone of this space. This means that we shrink this metric space many times, and if it was unbounded, it remains unbounded, and let us find in some sense limit of this space. Yes, here we have only conjectures with some hints. Yes, this, for example, for Euclidean space, we obtain the same space. For the hyperbolic space, we obtain a tree, which is very dense, it branches at every point. Yes, and here for this group, we obtain something strange. We obtain some coincidence. There are some parts, subspaces, which have the structure of tree, and some parts which have the structure of linear of Banach spaces. And they are very complicated, in a very complicated manner, joined in this space. So we have some very interesting space. And the problem is, what is the asymptotics of the geodesics in this space? The fluid flows are geodesics in this space. Yes. Here we have some interesting situation. What is proved for this? What is rigorously proved for this dynamical system in this space? First of all, it was proved that there exists a wandering domain. There exist wandering domains. There is Nadirashvili. This means that there exist domains that are driven by the flow, and they do not return back. So intersection of the image of this domain with its initial domain is 0 after some time. So this is, here we have, excuse me?
It stays 0 after.
Excuse me?
It remains 0 after some.
Yes, after some time, the intersection remains 0. Yes. The next result. Yes, sure. Because there is no way to go very far in this domain M, but there we may go far in the yes, in the derivative space. Now the next result is that there exists a Lyapunov function What is this? Lyapunov function, consider the arbitrary dynamical system with a phase space x, such that x dot equals fx is the dynamic equation first order defining this dynamical system. Lyapunov function is a function Lx such that it grows along every trajectory. So if we have such a Lyapunov function, this means that we have in some sense the dynamical is trivial. That almost all trajectories, or typical trajectories, are going in the direction of growth of this Lyapunov function, does not return. So there is no cycles, no non-trivial invariant sets, and so on. This means the conjecture is that in this dynamical system, it has very few or even no closed orbits, and in a sense it's trivial. Yes, but this is only if we look at the behavior of this system in this phase space. But we can consider only the vector field, velocity field. In a sense, it's one component. Yes, in this component, the behavior is believed to be, and this is a problem, quite opposite. Here, in the space of velocity fields, we have some very strange attractor, which is some infinite dimensional set consisting entirely of fixed points, of stationary flows. Yes, and the conjecture, which is maybe exaggerated, but it's close in spirit to what physicists think, that the generic flow tends to this attractor. Either it tends to some point of it, or it tends to attractor and moves very slowly. It is not. It is compatible because this Lyapunov function is defined in the phase space with element G and U. Yes, and we observe here only U of P, only one component. Yes, yes. Why it is compression here? It is compensated by expansion in other direction, because the diffeomorphism group is very fast growing at infinity, and so there is plenty of space where to spend the entropy. Yes, and so all this stuff is now in the state of hypothesis and very few results, but I think that it has some future. Thank you. Oi.
Talks or questions? Yeah, после.
Then you have to remember exactly what you're talking about. The collection.
Yeah, maybe people kept some questions inside, so now they can just formulate them. Okay, if not, then maybe Professor Hofer can explain again his result to people working in dynamical systems so that they can really see what was actually proven.
Well, well, I was, of course, a little bit under the time frame. So, using holomorphic curves, one proved the existence of certain surfaces. Oh, yes. Okay, so
using holomorphic curve methods, I said, well, I stated a theorem which tells you that in the complement, that if you have a generic Rebbe vector field, then in the complement of a finite number of periodic orbits, you can make a foliation which is... No, within the Rebbe. Within the Rebbe. Oh, okay, so you start... So you start with a contact form, and you multiply by a function. Then it's basically a Hamiltonian together with a geometric condition. So you start with a contact form. You're allowed to multiply by a function f, let's say. Then for a bare set of such functions, the periodic orbits are non-degenerate in the sense that if you take a transversal section, takes a return map, linearize it, one is not in the spectrum and also not for all the iterates. You can find a Hamiltonian which computes with that is you can you could find it. You have an energy surface. You could find Hamiltonian having as an energy surface commuting with a relation that would be equivalent. So now let me formulate now in dynamical terms, forgetting about the method using holomorphic curves. In the case of S3, what the conditions are, and then let me comment how you could generalize it, because otherwise it gets a little bit out of hand. So we consider contact form of this type where this is a standard contact form, and we were on S3 and we look for the dynamics of the associated Rebbe vector field, which is defined by these two conditions here. So now we want to generalize the notion of a surface of section. So in this case, a global system of surfaces of section is now, I assume that this is non-degenerate, so the periodic orbit are non-degenerate, consists of, is the following, or consists of a smooth foliation of dimension 2 of S3 minus a finite number of periodic orbits which has a certain number of properties. So each leaf can be compactified by adding some of those orbits. So that means the leaves are actually parametrized by punctured surfaces. If you run through a puncture, you run to a periodic orbit. So and you compactified by adding them. So each leaf can be compactified by adding some of these periodic orbits. Then a leaf is transversal to X, to the flow. Then near, so let me call them here spanning orbits, for obvious reasons. They span the surface. So near a spanning orbit with, let me write identity P prime positive, so that is the return map, linearized. I look at the identity minus P prime. If this is positive, that would be the case if the periodic orbit is elliptic, or it is hyperbolic with non-orientable stable and unstable manifold. Then the foliation looks like this topologically. This here is a periodic orbit coming out of the blackboard. Suppose this identified with the beginning, and that is a trace of the foliation. Then if, so A, be near a periodic orbit with this negative, which are precisely the hyperbolic orbits with orientable stable unstable manifold. The picture is like this for the foliation, topologically. And there, let me also draw the stable unstable manifold. The position would be then something like this, topologically. That is the foliation near such an orbit. Then so I think one has to impose the following, namely, suppose you have an orbit which hangs around this for a long time here. Then principally, of course, it could run along this periodic orbit here which comes out, and so it hits, is transverse to the surface, but it doesn't go through all the surfaces. I think that is... Yes. So the vector field would be transversal to it, but it could be that it's sort of, they have an orbit which sort of closer and closer goes to it. Perhaps, well, it takes maybe some time because it's linearized, it's hyperbolic, but so it could, now it goes in this direction so that it doesn't really go around. So I want to go that it goes around. So for each periodic orbit there's a number t, and if t0, and if I longer there for t, then approximately I go t divided by t0 times around. Yes. No, that I want to have. Yeah, so I think I have to require this. Yeah, these are requirements. So let me just formulate it as nice near, let me call this even orbits here, even, and this odd orbits, near even orbits. Yeah, so maybe one has to require this. Then, now, concerning, now so now you have here different type of surfaces. So what I want to have is that there's a finite family of those surfaces which can be parameterized by one parameter, S1 or an open interval, so that its type doesn't change. It means they all have the same compactification and they all have the same type. And these things then degenerate in a precise way, where I'm going to draw a picture, and the union of these families plus the degenerations is the whole foliation. Yeah, I think, yeah, it is, for example, true if you have, for example, an open book decomposition, then you can definitely find a context structure where the binding orbits are periodic orbits and the real vector field is transversal. That's true. So I think it might be even true under this more general conditions. So if you have a surface of section, globally, that's possible. So there exists a finite number. So what I want to say is that I can take part of the foliation. Yeah, it's sort of difficult to formulate. So I can parameterize a pile of these leaves as a finite family, which then parameterized either by S1, then actually if M is connected, only be one such family, or by intervals. And if I run to the end of the intervals, it degenerates in a certain way. So there exists a finite number of one-dimensional families of leaves, finite number of smooth one-dimensional family of leaves, parameterized by S1. If M is connected, then it's over, or then there's only one family, or by I, the open interval, so that near the boundary of I, one has this type of degenerations. Maybe I could even require more, but so let me say here can be by adding finite number of periodic orbits. Here I say these are periodic orbits with a minimal period. In general, you could actually allow them with a multiplicity, and if you compactify them with multiplicity, which, for example, you have to do in RP3 or something like this. So near the boundary of I, then we have such decomposition. So we start with something like family, and then it could degenerate like this. So these are the same orbits here, AB, AB, and then what you could get is a separation of a disk and to get a new orbit, which would be again a spanning orbit. Or that could also happen if I have genus. And the other would be that, so I start again with a surface, and it could decompose, for example, like this. In two parts always. Yeah? So falls apart or it creates a new orbit. Yeah? So that would be. Well, in my picture on Reshnikov, but I could require that in this generality. And then the theorem was that if I'm in S3 with this structure, I can find something like this, where these are actually all coming from rational curves, where you have one boundary component which is orientationally preserving map to the periodic orbits, all the other orientation reversingly, and then also having the fact that I have the form d lambda, then d lambda induces on all those surfaces by this transversality condition volume forms, and then using this structure, you can, for example, prove this result if stable, unstable manifold intersect transversally, that I have to be, for example, precisely 2 or infinitely many just by area considerations. And I think then this can be generalized, for example, by allowing multiple covered periodic orbits. If you compactify, so you might have that the surface of compactified covers the periodic orbit several times. Then if you glue two things together, there could be different families having the same splitting, but viewed with a different gluing and so on. So there are plenty of possibilities how to generalize this. But that would be sort of maybe the easiest definition, and that should be viewed as a generalization of a surface of section. Yes. Or a little bit more general, I mean, if I would have a surface of section, I would have only, I mean, the whole thing would be foliated by the same type. But I have this possible degenerations because what actually is the only obstruction to the existence of a surface of section is you start with such a surface, and if it would be a global surface of section, you could move it by the flow and it would exhaust the space. However, then, the obstruction is that you have some periodic orbits there which don't go through this and it decomposes there. And then you just have to compile this in a sensible definition, and that can be proved that such things exist.